I could read. I can see her slides, but audible.
So, sir, can you hear me?
Yeah. I'm able.
Yeah, so you can, Santamarai, please go ahead.
Yeah. Uh, so today the speaker is Arpita Nayek from Chennai Mathematical Institute. She will talk on Torus quotients of Schubert varieties in the Grassmannian G2N. Yeah, Arpita, you can start.
Thank you, sir. Uh, so, our research work is about, here we consider the action of a maximal torus T of SLNC on the Grassmannian G2N, where n is a positive even integer. And we study the GIT quotients of the Schubert varieties in G2N. Here we prove that the GIT quotient of the minimal dimensional Schubert variety admitting stable points in G2N is the projective space e to the power n by 2 minus 1. Further, we prove that the GIT quotients of the Schubert varieties in G2N have finite singularities. So first I will give some notations. Throughout our slides, I will consider G as SLNC and T be a maximal torus of G, R be the set of all roots with respect to T, R plus be a set of all positive roots, be a set of positive roots, and T contained in B be a Borel subgroup of G corresponding to R plus, and S equal to alpha 1, alpha 2, 2 dot 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 alpha n minus 1 denote the set of all simple roots in R plus, and W is the normalizer of T in G quotiented by T with a Weil group of G with respect to T. So for a subset I of S, we consider the parabolic subgroup of G generated by B and n alpha such that alpha belongs to I by Pi, where n alpha is a representative of S alpha in normalizer of T in G. We denote Ps minus I by P to the power I upper I. In particular, Ps minus alpha R is denoted by P alpha R, called the standard maximal parabolic subgroups of G for some 1 less than equal to R less than equal to n minus 1. Let WPI be the subgroup of W, Weil group, generated by S alpha such that alpha belongs to I, the Weil group of Pi. For I subset of S, W to the power Pi equal to W belongs to the Weil group such that W of alpha belongs to R plus, the set of positive roots, for all alpha belongs to I, at the minimal posterior representative of W mod WPI. Let IRN equal to A1, A2, we take the tuple A1, A2 dot dot AR such that 1 less than equal to A1 less than A2 less than less than AR less than equal to N. And there is a natural order preserving identification of W to the power P alpha R with I of Rn, and the correspondence is given by W belongs to P alpha R mapping to W of 1, the tuple W of 1, W of 2 dot 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 W of R. Grassmannian variety GRN is the set of all R-dimensional subspecies of Cn, and the Grassmannian variety GRN can also be identified with the homogeneous space HLN mod P alpha R, where P alpha R is the maximal parabolic subgroup corresponding to the simple root alpha R. So here we define the Schubert variety. For W belongs to WP alpha R, the closure of the B orbit passing through WP alpha R in G mod P alpha R has a natural structure of a projective variety, and this is called the Schubert variety associated to W, and it is denoted by X of W. So let EI such that 1 less than equal to I less than equal to N denote the standard basis for Cn, and let EI bar equal to EI1 waste product with EI2 waste product dot 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 waste product EIR for I bar equal to I1 I2 dot 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 IR belongs to I of Rn. Then EI bar such that I bar belongs to I of Rn forms a basis of lambda RCn. Let Pi bar such that I bar belongs to I of Rn be the dual basis of the basis EI bar such that I bar belongs to I of Rn. Then pi bars are called the Blocker coordinates. And note that this pi bar restricted to xw, x of w, the Schubert variety, is non-zero if and only if I bar less than equal to w of 1, w of 2, w of r. The monomials p tau 1, p tau 2, p tau m belongs to h naught x of w, L of omega r tensor m, where tau 1, tau 2, tau m belongs to I Rn are said to be standard monomials of degree m if tau 1 less than equal to tau 2 less than equal to less than equal to tau m less than equal to w. And the standard monomials of degree m on x of w forms a basis of the space of sections h naught x of w L omega r tensor m. Here we define semi-stable and stable points. Let L be a T-linearized ample line bundle on G mod P. We also denote the restriction of the line bundle L on x of w by L. A point P in x of w, Schubert variety, is said to be a semi-stable point with respect to the T-linearized line bundle L if there is a T-invariant section S in h naught x of w L tensor m for some positive integer m such that h of p is non-zero, and we denote the set of all simple semi-stable points of x of w with respect to L by xw SST of L. And a point P in the set of all semi-stable points with respect to the line bundle L is said to be stable point if T orbit of P is closed in the set of all semi-stable points of x of w with respect to the line bundle L and the stabilizer of P in T is finite. We denote the set of all stable points of x of w with respect to L by xwst of L. Let x be a projective variety in Pm, and we denote by x cap the affine cone of x. X is said to be projectively normal if its affine cone is normal. And for the practical purpose, we need the following fact about the projective normality of a polarized variety. A polarized variety XL, where L is a very ample line bundle, is said to be projectively normal if its homogeneous coordinate ring direction k greater than equal to 0 h naught x L tensor k is integrally closed and is generated by h naught xl as k algebra. So here we get a lemma on the GIT quotient of the minimal dimensional Schubert variety admitting stable points. Let G be a simple algebraic group of rank L. Let chi be a non-trivial dominant character of T, and let chi be equal to summation I equal to 1 to L m I omega I. Let I equal to alpha I belongs to the set of or simple roots such that m I greater than equal to 1. Let p equal to p to the power I, and let a belongs to n be such that a chi is in root lattice. Then let w belongs to wp such that w of a chi is equal to summation I equal to 1 to L a I alpha I, with a I less than equal to -1 for all 1 less than equal to I less than equal to L. Then the set of all stable points of x of w with respect to the line bundle L of chi is non-empty. So due to a theorem of Howard, Milson, Snowden, and Buckel, and using the Gelfand-McPherson correspondence, we get that the GIT quotient of a set of all semi-stable points of G to N with respect to the line bundle L n by 2 omega 2 quotiented by T is projectively normal with respect to the descent of the line bundle L n by 2 omega 2. And a corollary to this theorem is the GIT quotient of a Schubert variety in G to N for the action of T is projectively normal with respect to the descent of the line bundle L n by 2 omega 2. So here, this is a minimal dimensional Schubert variety admitting semi-stable points. Let WS's minimum, this is equal to Sn by 2 minus 1 S1 multiplied with Sn minus 1 S minus 2 S2 equal to, in one line notation, it is n by 2 comma n, and this WS's minimum is a unique minimal element in W power S minus alpha 2 such that WS's minimum of n by 2 omega 2 less than equal to 0. And therefore, by a theorem of Kannan and Arpita Nayek, we get that the Schubert variety H of WSS minimum is the minimal dimensional Schubert variety in G2N admitting semi-stable points. And we note that we have seen that product of k equal to 1 to n by 2 pk n by 2 plus k is the unique standard polynomial in H naught of x WSS minimum L n by 2 omega 2 t. Therefore, this Torus quotient of set of all semi-stable points of x of WSS minimum with respect to the line bundle L n by 2 omega 2 is a point. Because of this is the unique standard monomial in this t invariant section. Okay. So let WH minimum equal to S n by 2 minus 1 dot 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 S1 multiplied with S n minus 1 S minus 2 dot 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 S2 equal to n by 2 plus 1 comma n, and then WS minimum is a unique minimal element in WS minus alpha 2 such that WS minimum n by 2 omega 2 is strictly less than 0. Therefore, by our lemma, that previous lemma, we get that X of WS minimum is the minimal dimensional Schubert variety in G2N admitting stable points. And here we have seen that the standard monomials in H naught x WS minimum L n by 2 omega 2 t are xt, which are in the form of P1t product over k equal to 2 to n p minus 1 p k n by 2 plus k product over k equal to t to n by 2 p k plus 1 n by 2 plus k for all 2 less than equal to t less than equal to n by 2 plus 1. And the GIT quotient of GIT quotient, Torus quotient of the set of all semi-stable points of x of WS minimum with respect to the line bundle L n by 2 omega 2 is isomorphic to p to the power n by 2 minus 1. So let r equal to direct sum d greater than equal to 0 r d. Here we give the proof, and we take r equal to direct sum d greater than equal to 0 r d, where r d equal to h naught x WS minimum L n by 2 omega 2 t invariance.
Something is missing there. Hello?
Hello, sir.
Something is missing in RD. There, D is not there.
Yeah. Sorry. So it will be L n by 2 omega 2 to the power tensor d.
Tensor D. Okay.
So then Torus quotient x WS minimum, Torus quotient of set of all semi-stable points of x WS minimum with respect to the line bundle L n by 2 omega 2 equal to approach r. Then r is denoted by xt 2 less than equal to t less than equal to n by 2 plus 1 as a C algebra. On the other hand, since the Schubert variety x of WS minimum admits stable point, so here we see the dimension of x WS minimum is equal to n by 2 minus 2 plus n, and dimension of t is n minus 1. So its dimension is equal to n by 2 minus 1. So therefore, R is a polynomial generator. And again, we have seen that R is generated by these xt's 2 less than equal to t less than equal to n by 2 plus 1. So therefore, R is the polynomial algebra generated by xt 2 less than equal to t less than equal to n by 2 plus 1. And hence we get this flow chart is isomorphic to p to the power n by 2 minus 1. So okay, so there we just recall the Flocker relations. The Grassmannian G2N is a closed subvariety of p to the power n minus 1, where n equal to nc2 given by the Flocker embedding. We recall the Flocker relations for G2N, which will be used later. The Grassmannian G2N consists of zeros in p to the power n minus 1 of the following quadratic polynomials PIL Pjk minus Pik Pjl plus Pij Pkl, where 1 less than equal to I strictly less than k, j strictly less than k, strictly less than l, less than equal to n. So we'll use this Flocker relation to see the relations. Let x equal to Torus quotient of set of all semi-stable points of G26 with respect to the line bundle L3 omega 2. And let R equal to direct sum d greater than equal to 0 Rd, where Rd equal to h naught G26 L tensor d 3 omega 2 t, and x equal to approach R. So Rds are finite dimensional vector spaces, and let x1 equal to P14, P25, P36, x2 equal to P12, P35, P46, S3 equal to P13, P25, P46, X4 equal to P12, P34, P56, and X5 equal to P13, P24, P56. Then the set X1, X2, X3, X4, X5 forms a basis of R1, and let R tilde equal to the polynomial ring generated by X1, X2, X3, X4, X5. We get a lemma that using this relations above Blocker relations, that f of x1, x2, x3, x4, x5 equal to, if we take f of x1, x2, x3, x4, x5 equal to x3, x4 square minus x1, x2, x5 plus x1, x3, x4 minus x2, x3, x4 plus x2, x3, x5 minus x3, x4, x5.
Just
So
explain, just hello.
Hello, sir.
Just to explain that, just go back to that Prucker relations and then show that, show it for some time. People can look at it. That relations, Prucker relations.
Okay.
Because that you are using here, no?
Yeah. So this relation we are using again and again, that PIL PJK minus PIK PJL plus PIJ PKL equal to 1 less than equal to I, strictly less than J, less than K, less than L, less than equal to N. So
So using that, you get that f of
yes.
something is 0, no? That
Yes. So using that, we are getting the relations between x1, x2, x3, and x4, x5.
so it's given by a single equation, this case.
Yes. So and this equation also is an irreducible polynomial. Sorry, this polynomial is an irreducible polynomial in R tilde. And let I be the ideal generated by this polynomial f. And since I is generated by irreducible element and R tilde is UFT, so I is a prime ideal in R tilde, then R tilde mod I is an integral domain. Let pi from R tilde to R tilde mod I be the natural surjective homomorphism of C algebras, and let phi from R tilde to R be the C algebra homomorphism defined by Xi to capital Xi, and phi induces C algebra homomorphism phi tilde from R tilde mod I to R. And we note that the set of all stable points of G mod P alpha 2 with respect to the line bundle L3 omega 2 is non-empty. So therefore, from the dimension count, because of that dimension of G mod P alpha 2, it will be equal to 8, and dimension of T, that is equal to 5. So here we gave the full dimension of R is 4. And also because of that I is generated by single polynomial f, so the full dimension of R tilde mod I is 4.
Just
So therefore,
explain both why they are 4. Maybe the ring part Arpita follows from that single equation, and
yes,
the
and
number
the
of
full
variables is
dimension
5.
of R, so
But what
it
about
corresponds.
other dimension? The full dimension of R.
Yes, so G mod P alpha 2, its dimension is 8, because of it we can write down as
2
uh,
into 6 minus 2.
8,
R
so
into
5, 6.
R
Yes.
into n minus R. That
Hmm.
you are used to.
Yes.
Okay.
And
And
yeah,
the
and the
stable
dimension of
points.
torus is 5. Yeah.
And stable points is something like on the open part, it's a T bundle. So that looks like the dimensions are added. The fiber plus the base dimension will be equal to the dimension of the variety.
Yes.
Okay. Okay.
Okay. So we get the following lemma that phi tilde from R tilde mod I to R is an isomorphism of C algebras. We take here we study the torus quotient of x of 6, 8 in G to 8. So similarly as the previous one, here R equal to direct sum D greater than equal to 0 RD, where RD equal to H naught x of 6, 8 L tensor D for omega 2 T. And we note that x equal to proj R and RDs are finite dimension and vector spaces. Let x1 equal to p12, p34, p57, p68, and x2 equal to p12, p35, 47, 68, x3 equal to p13, p25, p47, p68, x4 equal to p13, p24, p57, p68, and x5 equal to p14, 25, 37, 68, x6 equal to P14263758, x7 equal to 13264758, x8 equal to 12364758, and x9 equal to P15263748. So here the set x1 to x9 forms a basis of R1, and we get the following relations in R2 using the Blocker relations. So there are 5 relations, and here we have used maculae to see that ideal I generated by the above relations is a prime ideal in the ring R generated by x1, x2 to x9. And also we have seen that using maculae 2, we have seen that the rule dimension of R mod I is 5. So here also the proof goes similar in a similar way. We note that R is a graded C algebra which is an integral domain and generated by R1 elements xi 1 less than equal to I less than equal to 9, and let A equal to the polynomial ring generated by x1 to x9, and let I be the ideal of A generated by the above relations mean the above ones. Then I is a prime ideal of A, and therefore A mod I is an integral domain, and let pi from A to A mod I be the natural surjective homomorphism of C algebras, and let phi from A to R be the C algebra homomorphism defined by xi to capital Xi. Phi induces C algebra homomorphism phi tilde from A mod I to R. So here also from the dimension count, we have seen that because of the set of or stable points of x sub w with respect to the line bundle L4 omega 2 is non-empty. So yeah, from the dimension count, we see that the rule dimension of R is 5. And on the other hand, using maculae 2, we have seen that rule dimension of A mod I is 5. So we get the following lemma that A mod I to phi tilde from A mod I to R is an isomorphism of C algebras. So this is the study. We study that Torus quotient of x of 710 in G210. And here also the proof goes in a similar way as above 2. So here we get total 14 sections here, x1 to x14, and here we get total 21 relations between xi's in R2. And also we use maculae to see that ideal I generated by the above relations is a prime ideal, and the full dimension of R mod I is 6 here. So because of that set of semi-stable points of x of w with respect to the line bundle L5 omega 2 is non-empty. So therefore the full dimension of R is 6. This will come from the dimension count of w and of x of w and t. And on the other hand, we have seen that full dimension of A mod I is 6 by maculae 2. So therefore we get the lemma that phi tilde from A mod I to R is an isomorphism of C algebras. Okay. So we come to singularities. Let H be a simple algebraic proof over algebraically closed field K, and let Q be a minuscule parabolic subgroup of H, and W be the Weyl group of H. Let WQ be the minimal quotient representative of W mod WQ. For W belongs to WQ, let X of W be the Schubert variety in H mod Q corresponding to W, and let X of W smooth be the smooth locus of X of W. Then due to a theorem of Brio and Polo, we get that let W belongs to WQ and let PW be the stabilizer of X of W in H. Then the smooth locus of X of W, this is equal to PWWP quotiented by P, which is contained in X of W. And
just 1 second. You can explain what is the meaning of minuscule.
Yeah, that is that omega I alpha
maybe
I less than equal to 1.
Maybe with the example SLN all the.
SLN all the weights are minuscule.
All the fundamental weights are minuscule.
Yes.
Huh?
Yeah. So let H equal to SLNC and Q equal to P alpha 2 and W belongs to WQ be such that Ws minimum less than equal to W in WQ. Let x equal to Torus quotient of the set of all semi-stable points of x of W with respect to the line bundle Ln by 2 omega 2, and let phi from the set of all semi-stable points with respect to the line bundle Ln by 2 omega 2 to the Torus quotient x be the GIT quotient map, and let y equal to t quotiented by x of WST Ln by 2 omega 2. So then we get that since this x of set of all semi-stable points of x of W with respect to the line bundle Ln by 2 omega 2 minus the set of all set of all stable points of x of W with respect to the line bundle Ln by 2 omega 2.
This y is x, right?
Sorry, no, it is actually wrong. It has to be x of
Oh,
W. Means the Torus quotient of x of W is t.
okay, yes, stable point.
Yeah, there is a confusion. See, the x you are using here, xw, that notation is confusing.
Yeah.
That should be xws, no?
Yes. Hi, sir.
Huh?
Yes. It has to be x of WST. This is the set of stable points of x of W with respect to the line bundle Ln by 2 omega 2.
And for any w greater than or equal to w min s, no? That one?
Yes.
Okay. So it should be xw, not xw min s. It should be xw upper s.
Yes.
Bracket and then further s. Yeah. There are two notations. Yeah.
So, okay. So since the set of all semi-stable points of x of W with respect to the line bundle Ln by 2 omega 2 minus the set of all stable points of x of W with respect to L by 2 omega 2 is a T-invariant closed subset in the set of all semi-stable points. So we get that x minus y is a closed subset in x. So that means y is open in x, and then we get the following proposition that all the points of y are smooth points of x. And the next proposition is if xi is a semi-stable point of x of ws is minimum with respect to the line bundle Ln by 2 omega 2, and let k equal to p belongs to W to the power p alpha n by 2 such that b xi belongs to union of WSS minimum less than equal to u less than equal to W, b eq mod q, and L equal to phi of v xi such that v belongs to k. So then the set of all singular points of x is a subset of L. So here we see that so x, the set of all singular points of x is subset of L, so that, and L is parameterized by k, which is a finite set. So that's why we get the corollary, the set of all singular points of x is finite. Here we come to an example. The Torus quotient of set of all semi-stable points of G to 6 with respect to the line bundle L3 omega 2 is not smooth. So let x equal to Torus quotient of set of all semi-stable points of G to 6 with respect to the line bundle L3 omega 2, and we have already seen that x is a cubic hypersurface in the projective space before in the slides, which is given by f of x1 x2 x3 x4 x5 equal to x3 x4 square minus x1 x2 x5 plus x1 x3 x4 minus x2 x3 x4 plus x2 x3 x5 minus x3 x4 x5. Now we consider the affine open cover A4 of P4 defined by x1 not equal to 0. Then we get f of y1, y2, y3, y4 equal to, just dehomogenizing this f, that f equal to x2 by x1, x3 by x1, x4 by x1, x5 by x1, and we get the polynomial y2, y3 square minus y1, y4 plus y2, y3 minus y1, y2, y3 plus y1, y2, y4 minus y2, y3, y4. Let xi be a point. The set of all semi-stable points of B of WS is minimum P alpha 2 mod P alpha 2 with respect to the line bundle L3 omega 2, and phi of xi equal to P, where P equal to 1 0 0 0, where P tilde is 0 0 0 0 because we have already taken x1 is non-zero. So be a lift of P in the open cover of x. Then we have del f by del y1 equal to y4 minus y2 y3 plus y2 y4. Del f by del y2 is equal to y3 square plus y3 minus y1 y3 and plus y1 y4 minus y3 y4. Similarly, we get del f by del y3 and del f by del y4 as a polynomial in y1, y2, y3, y4. And because of this p tilde equal to 0, 0, 0, 0, so we get del f by del y1 of p tilde, del f by del y2 of p tilde, del f by del y3 p tilde, del f by del y4 p tilde equal to 0, 0, 0, 0. So that's why we get that p is a singular point of x.
And how many singular points are here? By your thing is finite.
Sorry?
No, how many singular points are there in this case? Because it is the complement of that stable point smart t, is it correct?
Yeah.
So the w orbit of that point, that p network. Okay. Because w will act on the quotient, t invariance. So therefore that will act on the variety, and therefore it will act on the singular locus of the variety. Yeah. So therefore w orbit number of it will be there.
Okay.
Proceed.
Okay, sir. So, sir, that
And
was yeah, sir. So now we are done here.
any questions? Hello?
Can you show me once again the main theorem, that first slide, the statement one?
Yeah. So, do you mean this one or?
Yeah. You said something about projective normality. Oh, that is for those specific Schubert variety.
Yes.
I see. Okay, thanks.
Any other questions? Hello? Okay, if there is any, there is no, hello? Yeah, any questions? Okay, if there are no questions, we can, hello? Everybody wants to say something? Hello? There are no questions, we can thank the speaker. Okay.